1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
Yeah.
That was the.
Yeah, we're good now.
We're good now?
Yep, you're streaming. You're on.
We're streaming? That was the magic squares. Apparently, I found kids' tiles in the store and I bought those because I was like, I could use those for 3x3 magic squares. There's the original 1, 2, 3, 4, 5, 6, 7, 8, 9. I can count to 9 at least. And then there they are rearranged into the magic square. I don't know why I own these. Scat. You know what Scat is? It's a German card game. Scat. It's not what I thought of when I said scat the first time. I see some deer scat. Are we on Twitch and the other one? Just a second. We're on both. Hello, everybody. Just a second. Let me turn my computer on because we're ad hoc. I'm not ready. I'm supposed to do a live stream today, but I don't really want to do it with freaking a book company. There's Twitch. Are we on Stream Manager? Can I see myself? Let's go. All right, what I was going to do was last time, and then we were just checking that it works. But now we can actually do this. Let's see if I can do this where I keep my coffee. Oh. Tim, I blame Tim immediately. I don't even know if it's him or not. What are you watching commercials for? I know. I'm just going to blame him either way. I know 50% of the time I'm right, 50% of the time I'm wrong, but I'm blaming Tim every time, just like when you go to work. Let's do hashtags. We got to start doing hashtags too. So the first hashtag I want to do is, this is called an octothorpe, but in hashtag octothorpes, everybody. But in Mobius geometry, this is congruent to our new Tutor wizard symbol, which is the octothorpe in Mobius geometry, which is this. So that is the same as this, or congruent, and let's see how that happens. This is also, I think, if you remember, this is what I gave to Siobhan on her final exam. So let's make this specific. Let's do it like this, and then we'll do the 4 lines we're gonna do. I'll probably only do 1 or 2 lines. On the board, everybody, on the board. So, what are these guys? Let's call this. So, we're in the complex plane. That's the joke, right? Do you know complex variables? Lorenzo does a little bit. Have I told this joke already? Yes, but I'm a dad, so I'm going to tell it again. It's the Allies against the Axis, World War II, the second one. The Reckoning. F around and find out. It's like you don't need to come up with subtitles for the thing. Everybody knows what you're talking about. But there's a Polish guy, and we're going to leave the Americans out of it too. Oh, kitty. Hi. Small cat. Let's hold a cat while we tell this story. Hi. You heard us talking? This one's Mud. Hi. You're a good boy? You're going to go see the other boys? They're over there. Yep. No, you love me? Hi. You just want me to pet you down there? There's a Canadian and a British soldier and a Polish soldier, and they're being chased by the Nazis, and they're in an airfield. So then they see an airplane. So then they run towards it, and they get into the airplane, and they're like, who's going to fly? I don't know if there's more lead up to this joke or not, but I don't remember any of it. So I'm just going to tell mostly the punchline. And so, for whatever reasons, the Polish guy, they get the, I don't know why you would do that, actually. Let's be derisive towards the Polacks. But the Polish guy ends up in the driver's seat of the airplane, and then they're like, the Nazis are almost there, and the Canadian and the British guy are like, hurry up, and he's just like, hang on, I'm just a simple Pole in a complex plane. Funny. Which means you divide by 0 once. That means that they've heard that before and it wasn't funny the first time, so stop telling the joke. Guess what I'm telling next stream, and for every stream from now on, I'm just going to start the stream by telling that joke. I'll show you. So, we could make these 1 specifically, but I'm going to make it K, okay? So that you can see the formula. If you make it a 1, it'll disappear in the formula, which is also useful when you do a lot of things. When people do the special case of x squared plus y squared equals 1 squared, that loses the kind of the formula when you do this for r squared or rho squared. So you want to keep the r to see when you do this, to keep the r and see where it happens in the formula. With the 1, it usually disappears because I can write this, and then you lose a lot of information when you write the 1. So what we're going to do is I'm going to find, so what I want to show is the octothorpe, this specific one, is going to map to certain, these circle. Well, now I'm drawing something else. Just hang on a second. Let me let me fix the other thing I was drawing. I had to draw the centers of the circles. Okay, no. Now I'm just rubbing out the centers of the circles. It's like, damn it, that went backwards. That wasn't doing what I was supposed to do. But this is the white 4 octothorpe is the same as this guy. Why is that? Basically, what we can show is when our things can, what does it mean to have a geometry, and when our things are congruent. So in Euclidean geometry, which usually we do bottom up, Mobius geometry we do top down, which is the first thing that's just strange. So we're just going to talk about the differences. So Euclidean geometry is a subgeometry of Mobius geometry, and so is spherical geometry, or some of the non-Euclidean geometries. This is non-Euclidean. Euclidean geometry, you start off with axioms. So there's 1, 2, 3, 4. Don't make me list them, Mark, but this isn't the point. But the bottom up is, so there's one and only one straight line between 2 points, etc., etc. And then the 5th postulate, which is actually independent of this, is actually phrased this way. There's 2 different ways of phrasing it. But if you have 2 lines that are intersected by another, oh, it was empty. Tried to get me again. Stop putting my coffee there. The table is almost cleared off to where we can move it now. So I'm working on it. I'm working on it. It's close. We're close. And then so if you cut it like this, if the angles are less than 90 degrees, or if they equal pi radians, then they'll be parallel. If it's less than that, so if you draw the other scenario, somewhere out there, even if you can't see the intersection point, if you have that this is less than pi radians, then they will intersect on the side that they are less than pi radians. This one will have larger than pi radians, but they'll never intersect. They'll diverge, but they will converge into an intersection point. And so this is different in the Mobius geometry or the spherical geometry. In spherical geometry, parallel lines are great circles, and those great circles intersect at the poles. There's 2 parallel lines, but they do have intersection points, which is okay. But this is how you can tell that you're not in Euclidean geometry. The first 4 are independent of this, and then now this statement, why they focus on 3, Lobachevsky, Euclidean, and Riemannian are the word ones I would give, but I would give flat, which is Euclid. I would give spherical, which is the Riemann surface, which he did a lot of work, and now I don't know how to spell Lobachevsky. Close enough. Lobachevsky would be hyperbolic. This one's slightly different, and there's 2 ways of doing this, but if you look at M.C. Escher type of paintings, he has the demons and angels, and what happens is as you go from the center of the unit disk in the complex plane, the distances are logarithmic, so they get smaller and smaller. So the angels are big here, and then they get start smaller and smaller as you reach the point of infinity. So that's one way of doing this. The other way is using the complex plane. I'm not going to get into that one too much. But what we want to talk about is why are there 3 kinds, essentially. There are more than there's subgeometries, there's Euclidean geometry, and you can talk about rotational geometry or affine geometry, which Mark really likes, which is just translations. These are affine geometry. I had to say it too, dad puns. But so why is there 3? In Euclidean geometry, the 5th parallel postulate is equivalent to, in flat geometry, alpha, beta, gamma. The sum of the interior angles in any triangle has to be equal to what? Pi radians. or 180 degrees. In spherical, it's going to be more than that. That's why airplanes don't go across straight lines. They take those trajectories because if you're on the Riemann sphere or an oblate spheroid in space rotating around the sun, actually, that doesn't. It's a lie, right, Lorenzo? I'm gonna reference you when we do physics. The sun isn't rotating around or the sun is definitely not rotating around the Earth.
Planets orbit.
But the sun, if you just ignore all the other planets, the sun and the Earth are rotating about what? Their mutual barycenter or their axis of rotation. The sun is so freaking big that axis of rotation lies inside the sun. Jupiter, it just happened recently.
Where it's outside.
It's outside. The barycenter is outside the sun, so they're truly rotating around something. But that's how we first saw the first exoplanets. The red shift from that wobble. You want me to do that again? But anyways, so that's why when you're on the oblate spheroid, that they're going to take this. So the sum of the interior will be larger than 90 degrees. You'll get this. And then if you're on a saddle and you get the TNA symbol, you're going to have less than 180 degrees. So that's why you roughly have these three types of geometries called flat, spherical, or hyperbolic, or Euclidean, Riemannian, Lobachevskian. All right. So doing that, usually Euclidean geometry, the first time you see it because it's so ancient, we do it bottom up, which means you set up axioms and then you build the theory from this. But in this, when we do it top down now from Mobius, what defines a geometry? You need a set, and then on the Riemannian one, what we use is, which is the first good question that Lorenzo asked me when he was helping Siobhan, because he's like, I don't want to look like an idiot. I want to know what I want to make it look like I know. I want to make it look like I know what I'm talking about. Right. So it's like, which is also the first step to becoming SMRT. You have to admit that you don't know it, and then why are you taking the class? Otherwise you'd know everything. So why are we using stereographic projection? And this is the pullback and everything also. This is the copy of C, and instead of, and then Siobhan asked that question early on too, which is a good question. She's like, why do I want to know? Why do I have to know so much complex variables? So it's like, let's tie those two together. To do the Riemannian geometry or Euclidean geometry, to do all of these things that I'm about to do, etc., we need to know what complex algebra is, because what I do is I take the sphere S2 or the Riemannian sphere, and I can use stereographic projection for every P here. I have a point P hat here, which is AB, and then this is A, B, C, P hat. This is proper mathematics P hat, not this P hat that you guys are using in statistics. So what is the formula for this? S, which is bad notation, goes from S2 into C, and there has to be the North Pole is the special guy. Now we're just doing a whole crash course on Mobius geometry. It's like, yeah, use your PowerPoint, but let's tell a story, and then I don't know what unfolds. Let's see mostly if I know what I'm talking about. Comment in the freaking chat if you think I don't, or if you think I do.
Asking if this is tic-tac-toe, coincidentally, it's hilarious.
There's three kinds. Okay, we'll shift gears for a second. Yes, but this is a first player dominant game. If you know that there's a center square or there are side squares, or there's corner squares, or there are side squares. Up to symmetry, those are the same. So there's three kinds of squares. And what you're trying to find are critical triangles. One type of critical triangle is this. If you can put an object here, here, and here, then you're on the most, and this is why X is the most important square, you can argue, because it's on the most critical triangles. And you can do this. And so what you want to do is try and get the pincer move. So the only way to actually win in tic-tac-toe, if you're going to switch gears, is, I'm going to redraw that.
All right, and now that we've switched gears to tic-tac-toe, we're switching gears back. So you're measuring the shadow to see how round the sphere is?
No, I'm using stereographic projection to give a one-to-one correspondence or a bijection between this. So just a second. So yes, so in tic-tac-toe, in tic-tac-toe, the only way to make a mistake, but what you want to do is make a pincer move. If you can do this right in your moves, you win. Because if they put an O here, I get three in a row. So let's just a second. Let's do this one more. Now what you want to do is X's only. Tic-tac-toe. I'll play myself. So X's only means you can't use knots anymore, crosses and knots. So now we're just doing tic-tac-toe. Just a second. I like games, but I like this also. Now, what you want to do, X's only says if I put an X here, then that was player one. This is player two. The safest way to do this, which I really like, is to do a chess move away from this. So do the knight's move away from that guy. So I do that, and then that won't get me three in a row. That'll try and get me three in a row, and then say they have to block me. So then I'm going to block, and then if they know what they're doing, I'm doing this, and then this is going to be a draw now, right? Oh no, be careful. Be careful. I almost beat myself. Every time I do this, every time I beat myself, I win and I lose. So this was a draw again. So then what you want to do now to do this only is Merzer X's only, which means now if you get three in a row, you lose. So now let's try that. So now what I'm going to do is I'm going to do that, and then say they do this, and I'm going to do the knight's move away from that guy, and then the other guy, if he knows what he's doing, he should do a knight's move away from that, and then, oh, I don't want to do that because that would make a win, so then I'm going to do knight's move away from this. I'm not trying to win anywhere. That's where the Merzer comes from. And then now I don't want to get the three in a row, so he just went there, so I'm going to do knight's move away there, and then now the jig is up because the first player now has to put in one of those spots, and then no matter where I go, I get three in a row and I lose. So then what you want to do to tie that into that is you want to do Merzer only on three boards. And then I can use finite group theory to keep track of the moves that you want to do for this. And then I'll digress from this. In the first rule, if you get three in a row in the first two boards, you kill the board. You only lose if you get three in a row on the last board standing. And then I can use algebra with finite groups generated by A, B, 1A and B. I think it's there's three generators of a finite group, which is isomorphic to a permutation or a symmetric group of some kind. And then I can use the algebra to predict which moves I have to do. It's really hard to do in real time, but I can put it down on paper for you later. So let's move there to there. So now, why is Merzer only three board X's only tic-tac-toe better than original tic-tac-toe? Because I said, and because now someone has to win. There's no draws. Someone has to win. Now I'll go back to, don't tell me when I go back to the Mobius geometry. Now what he wanted to know was, do you remember why we want the stereographic projection? Should I throw you under the bus?
Yeah, you explained it like the sphere is a plane and the plane is C. I think that
right. And so what we want to do is, instead of having to do all of our algebra and computations on the Riemann sphere, we can find a one-to-one correspondence between C and then use complex algebra to do this. And then that ties into what Siobhan was asking, why do I want so complex? Because all of the algebra that we're going to use is complex inversion. So now, what is stereographic projection? What's the formula? So it's going to take A, B, C, and it's going to send it to a point, and it's going to be A over 1 minus C squared, B over 1 minus C squared. You can do the algebra, but that's where you send it. And then this is a bijection, and then you have to send the North Pole to the point at infinity.
You want to take a quick peek at this comment? Did you have your laptop?
Okay, yeah, I know. I've just been slowly let go, like the curling rock in Bill Burr's joke from Academia, so they don't like me anymore. But I like your comment. I like math. This is math with no lines. This is math with all lines. So now what we're going to do is we're going to use this stereographic projection, and now we can identify the Riemann sphere as a subset of the Mobius geometry. So now you need a set of objects. And then what do you remember the other piece of information we need? A geometry now. When are things congruent? We're congruent to objects. Let's do Euclidean geometry. When is this triangle? Hopefully I draw it identically. I said I hope you draw it identically, hand. There we go. That's better. I said no sideburns. Smithers, land the plane. Sir, you're driving. Spruce goose. So how is this? I did this upside down on purpose. So first of all, what I'd have to do is rotate it and then translate it. So the only types of translations you're allowed to use, I don't remember the notations that the book used that I used. I'm just going to make it E for Euclidean transformations. So E will be the set of rotational transformations, which are operators on from, these will be linear operators from, not all of them are linear because the fine ones are not linear, but this is from, I was going to use R2, but now we can use C, from C star, the closure of C into the closure of C. The closure of C has what I said, you need the North Pole sent to the point of infinity. So C closure is C union, the unique point at infinity. And so, and then now this is essentially because there's a one-to-one correspondence between the Mobius or the Riemann sphere and the C. We can also use this for Riemannian geometry. But the point being is, I might have had a couple Pepsis and a large coffee. Euclidean geometries are, just writing them in words, is the set of transformations that are rotations in the plane and affine or translations. And these days I refuse to shorten the word translations on principle. There's a joke there. Okay, so this is what unique. So unbeknownst to you, what you have to do is objects are what we call congruent if you could take them and make them coincide entirely. But how did you do that? You had to rotate them in some way if you think about it, and you had to translate them in some way. So this is the Euclidean geometry. You can prove, which I'm pretty sure I made Lorenzo and Siobhan do, is that there's two subgeometries of this. There is C star and just the rotational geometries. And then this one and the translations would be the affine geometry and rotational geometries, which are subgeometries of this geometry. So
right,
you need
I explained it to her as moving a clock on a wall. You have like the minute hand, right? And there's the rotation, then you're sliding around. There's the translation. I was quite proud of that.
And these are, yeah, and these are groups. And so the group axioms are what? It has to have an identity, which is the identity transformation.
Inverse.
Everybody has to have an inverse, G and G inverse, and then associativity. Yeah. Good. So these are groups. So what you need to define from top down to define a geometry is you need a set of objects that you're going to do this on. That's why the hyperbolic one is going to be the unit disk. And then the transformations, which are invariant under inversion. I won't get into that one. I think I said that wrong. But the hyperbolic geometries are the worst ones. These ones are all subsets of the Mobius geometry. So the Mobius geometry is going to be C, the closure of C, and then the Mobius geometries. And what are those? Do you remember? Which falls out of this. This is a subgeometry of this. And so there's the chart. And then the Riemannian geometry is going to come out of this one also, which is, I won't get into it, but I wanted to point out that whole rant accidentally because the Mobius geometry, the Mobius transformations are the rational linear ones. AZ plus B over CZ plus D, where all of these numbers are complex. And this is a Mobius transformation. These are all in C star. C star. You dunked my sister. I'm not allowed to say that. I just did twice. So that will create the Mobius geometry. So what I wanted to show was I had to do that rant. And then now, this is why you want me as your instructor, because I won't leave you behind. Now, if you've never seen geometry before, what I'm going to do is say that the octothorpe or the pound sign or the hashtag is equivalent to boobies rotated, two sets of boobies interlocking, my favorite kind. You didn't have to say it that way, but yes, I did. This is our symbol for our tutor wizard, two interlocking sets of boobies. It's like now it has to be. Now it has to be our motto. I don't even know if that's our motto. Yes, it is. That's our motto. Try to interlock those boobies. So stop saying it. What I want to do is why are they equivalent? What you need is a transformation which will map each one into this. So I'm going to use inversion 1 over z. And this is what Siobhan kept asking was why do we need complex variables so much? So let's take, without that, we're in the ambient space of complex, but this guy is going from C into C, this transformation, which is called inversion. I also made her do that on the first assignment. There's going to be 3 kinds of inversion in the complex plane based on whether the complex plane is what I get, is whether...
Yeah, that's apt.
Yeah.
There, complex plane.
This is without loss of generosity. And so here's the 3 kinds that you can have. I'm drawing them all in the first quadrant for simplicity. But you can have, we reference the unit circle. You can have that this one, if I did, so just to think about numbers. If I take 2, which is larger than 1, what happens to its inversion? It becomes 1/2. So it will go in here. If I take somebody that's inside that's less than 1, what if I take 1/2? What happens to the inversion of 1/2? It becomes 2. So then it will grow in the inversion. That's the kind you want, make it grow. And then what happens if you are on the unit circle? It's just a rotation, essentially, on the unit circle through this. So this is the type of getting to know what the inversion looks like. So what I did also here, because the inversion is two-dimensional to two-dimensional, I can't graph this. So I'm drawing the pre-image or the domain and the codomain on the same one. This is what happens to each of the vectors. And I did it in color so that you can see it. So now in 30 seconds or however fast I'm talking, that's roughly what inversion does to vectors. And now what I have to ask to myself is, what happens to this vertical line in the complex plane? So how do I describe this line? Also, there's a whole bunch of avatars. I just did this and I gave this in the linear algebra exam, but only talk about linear algebra. Don't connect it to another subject. That would be fucking painful. What I want to do is now, yeah. What I want to now do is notice that if this is in the complex plane, the x value is not changing. So we're going to call the x value constant plus iy. We have to call this. And then the y can change, and that describes the whole line. Okay, it's a different complex avatar of the vertical line. We're going to do the same thing for a horizontal line. That will be, the y won't change, so that'll be x plus I times k. And now what I want to see, let's do one of them, we'll probably be done. I'll leave it as an exercise. This is how you fake it till you make it. If you don't know, steal it from a wizard. So you're going to do the purple one. I'll do the white one. I want to say white is right, but I won't. And I want to see what happens to this under inversion. If I can see that this is why they're called clines. If I can show that the circle, this turns into a circle, then I can tell that those are equivalent. And then when you do 2 of them, you'll get 2 circles that do this, essentially, that will touch. And then if you do the 2 horizontal ones, you'll get them to do that. And then that's why that shape is equivalent to this. So I'm just building it one object at a time. Take it easy, take it easy. So we'll just do the one vertical object. And so then if I did the 2 of them, that's what I gave her on the final exam. I made the k equal to a 1, right? You're like, I don't know if I can remember. I had to grade it. She had to write it. Which one's worse? She got an A minus. Even for not that good of a student. In quotes, I didn't say that, Siobhan. I didn't say that. I didn't say it. The fuck are they going to do? Okay, let's see how that happens. This is quite exciting. Let's see if let's throw Tim under the bus now. Don't worry. All you need to do is, the key is viewing it 2 ways. In math, this is quite useful. He's like, you lost me at the frickin' stereographic projection. Okay, what am I doing? Don't lick it. It still tastes bad. I'm fighting off a sneeze, but I think we'll be okay.
You don't know where that chalk's been.
or I do, and it's just like, yeah, I'm a dirty. Someone, oh, that's a joke too. I was walking through the last exam, and this kid had a little thing that you put on your pens, and it had little eyes. Where is it? Then he'll know what I'm talking about. Yeah, this thing. And I every time I went through, I mentioned like 3 times how I really like that. You should just give it to me. And guess what? He had an extra one, and he said, "I'm like, where'd you get them?" He's like, my mom gave them to me." And so you can see where this is going, a mom joke. Should I do it? Probably. He's
Probably not.
probably not. It's a tame mom joke. He said, "Here, you can have this one that she gave me too, but this one's a little bit dirty." I was like, I didn't say it, but tell your mom I'm a little bit dirty too." There, I did it. I'll just say what I want.
That was as bad as I thought it was going to be.
No, it could have got worse, but he said this one, you can have this one, but it's a little bit dirty. I'm a little bit dirty too. If you ask nice, I bite. Okay, so we're going to view this 2 ways. In the one way, what I want is this is called Z classically in the domain, and then in the codomain, it has to be a W, which is the second way, which is clever. I stole this from Mark Solomonovich. I would have had no idea how to do this problem if I hadn't stole it from him and the book that we used. So that's the second way that I'm going to view this. On the other hand, what we have to do now is W is equal to, under this transformation, f of Z, which we're calling 1 over Z. So what that means is, I say sew a lot, stitch everything, don't sew it. I need to know what happens to 1 over Z, where Z is this guy. So that's going to equal 1 over K plus IY. Now, Tim, what's the question? Do you know how to find the inverse of a complex number?
Yeah, multiply by the conjugate.
Yeah, see, I wasn't throwing you under the bus like you do to me constantly with your hard problems.
You still got to learn how to play some Steely Dan.
Yeah, okay, yeah. I just meant with the frickin', I didn't give you frickin' an arbitrary, what was it? Lagrange multipliers, just cold. I gave you a nice one that you could knock out of the park, you prick.
Yeah,
Oh,
still did it.
I called you prick too. Don't do that because
I'm okay.
students like it when you call them pricks.
Yeah, but I'm okay with it. I know what I am.
So,
Ego death.
ego death. Oh yeah, yeah. If you haven't been knocked out, I'll be happy to oblige you. Zinc. Yeah, toxic. It's just masculinity. It's not. There's nothing toxic about it. So we're going to multiply by the conjugate. Why does that work? Because I have a denominator that has a complex number in it, which is bothering me. But if I multiply by the conjugate, that will be the modulus squared. So it'll just be a real number, and then I can do this. So that's why also you do the move. So now do you see what we did with this? I'll show you in a second. But this is K. It's like, good thing that Y is there. Otherwise, I just have KY. But this is going to give us K squared plus Y squared. And so the inversion with this vertical line is going to be K over K squared plus Y squared. And then minus or plus negative Y over K squared plus Y squared I. So there's that's what the image is going to look like. And then what I have to do is, why is that on a circle? So the dirty trick is, again, let's recap this in case you've never seen complex variables. I want to know what the inverse, or what K plus IY's inverse is. And C is a field. It's actually the algebraic closure of R. So every non-zero element has an inverse. So now what we're doing is, I don't like the I on the bottom, which bothers everybody. I is the square root of -1. So if we multiply by the conjugate, we get the modulus squared, the length of the vector squared. So now that gives us a real number, and then I can just push it through both, and then that gives us the complex inverse. So one way to view this inversion of this entire line is every point on that line is going to get mapped to here in the codomain. On the other hand, this is what it has to look like in the codomain. In the ST domain, it has to look like an S and a T. So now what we're going to cleverly do is we're going to call S equal to K over K squared plus Y squared. And T is equal to, by matching these complex numbers, this has to be negative Y over K squared plus Y squared. And now what I'm going to try and do is eliminate y from this and just get an expression in s and t and show that when I simplify that, it defines a circle with a center and a radius. That's where I'm going with this. So hang on, there's a lot of algebra about to happen. The first clever trick is if I divide these things, I can get rid of the k squared plus y squared. Negative y. I said negative, not equals y. So now I can get rid of the k squared plus y squared. This is like similar triangles, but a clever trick. See, the ratio of s over t is equal to negative k over y. Why is that good? Because I can now get rid of y. Y is equal to negative kt over s. And then I'm going to put it back in here. So I have equation 1, I have equation 2, I have equation 3 that I can use. I use the first equation to get rid of the k squared plus y squared. Now I could put it into either of these. Why do I pick this one? Yeah, there's only one y. Yeah, exactly. Exactly. It's like I helped you learn this class. This is good because the feedback of it, he's retaining it, so that means Lorenzo's SMRT, and I did a pretty good job teaching him, so it's like patting everyone's back. All right, so now what I'm going to do is put it back into here because there's only one y in there, and I'm trying to eliminate y. So this says now s is equal to k over k squared plus y squared is negative kt over s squared, and now you can see the circle appearing. Let's get rid of this. And I don't need this anymore. And so what did that do? Let's simplify this. This says s is equal to k over k squared plus, so we're going to multiply by s squared in a second, but I'll show you. I'll leave the space. And so this is k squared t squared over s squared. I need a common denominator, so I multiply by 1 of s squared over s squared. And then I can move the s squared up, and how am I going to do this? I just did this without an audience, and it was nice. Let's clean that up. That says s is equal to, what do I get? K, E, yeah, just wait, let me, yeah, you see it. K squared, s squared, but k squared. Okay, so let's factor that out. S squared plus t squared. And then that's over s squared, so that can go up to the top, right? Yeah.
Yeah, working through that the first couple times was.
It's like, what is he doing? But it's nice to know where you're going too, right? That's what I'm trying to show. I'm trying to show this maps into a circle, and then you can see the algebra. Now what I'm going to do is move the k squared up for a second to get rid of one of them, to show you that move. Okay, so now I have do it in slow steps, and then because now the s squared is by itself over s squared. Oh, I can get rid of one of the s's too, right?
Yeah. I was going to say that.
Yeah, okay, plus t squared. And then now move that up. That says s squared plus t squared is equal to s over k. You're going to get an sk in a second, Tim. Wait, what? I didn't do nothing. Now what do I have to do? I have to complete the square. When do I ever have to use the completion of squares when you want to show that in the Mobius geometry that a straight line, vertical line maps into a circle of radius, something, right shoe. S squared plus t squared minus s over k is equal to 0. How do I complete the square? Let's group this together. I have s squared minus 1 over k, or plus negative 1 over k s plus t squared is equal to 0. And so b is negative 1 over k over 2 is going to be over 2, and then square it, and that's what I have to add and subtract into there. And so that's going to give me s squared plus negative 1 over ks plus 1 over 2k squared plus t squared. I'm going to skip a step, and the negative 1 can go to this side. That's the radius now of the circle. And then I'm going to complete the square. This is s minus 1 over 2k squared plus t squared equals 1 over 2k squared. What is that? That's a circle with center 1 over 2k 0 equals 1 over 2k. Radius is 1 over 2k. So the vertical line mapped to a circle. If you actually map this out, the S was the horizontal, so that vertical line maps to this circle. The other vertical line will map to this circle. The horizontal line will map to this circle. The other horizontal line will map to this circle. Fucking. That's all I got.
Bazinga.
That's all I got for today. I'll do the other ones, but I got stuff to do in adulting and all that kind of crap.
Cool. Thanks, everyone. See you next time.
There you go. Mobius geometry and